Okay, in this recording, we are going to take a look at static equilibrium. Specifically, we're going to take a look at problem number 12.31 on the mastering. So in true static equilibrium, we know that for something to be in static equilibrium, that we need the summation of forces in the x direction to be equal to 0. There cannot be any motion. The summation of forces in the y direction must be equal to 0. There is no acceleration, and this is because there is no acceleration. But true static equilibrium also involves torque, rotation. The summation of torques around any pivot point must be equal to 0. That's because angular acceleration also equals 0. So we are going to consider directions in all of these. In the x direction, we will take to the right to be positive, to the left to be negative. In the y direction, we're going to take up to be positive, down to be negative, and with our torque, we're going to take clockwise to be negative and counterclockwise to be positive. So that is how torques, forces add up to be 0 because you have some in different directions. So going back and taking a look at this problem in mastering, we have this figure of a student standing on a beam with two supports, both at each end. The beam is 3 meters long. The student is standing 2 meters on the beam. There is no fixed hinges at either support. So the question is, where is the student standing and what is the forces upward on each one of those supports? So how much upward force does support 1 exert on the beam and how much upward force does support 2 exert on the beam? So because he is not exactly in the center, we must consider that he is closer to one support than the other. So as always, we will redraw our picture, list what we know, what we want to know, and begin with making these equations, these generic equations, fit our problem. So in our picture, we have our beam. We have our two supports over here and over here. And we have our person standing on the beam, located here, with the weight of the beam at the center of gravity. So if we were to draw a free body diagram of this, right, with all of the forces involved, we would have our beam. We would have support 1, which I'm going to call the normal force 1. We have support 2, which we're going to call the normal force 2. We will have the weight of gravity acting down from the beam. So the force of gravity of the beam. And they will also have the force of gravity of the student standing on the beam, right? So that is located over here. So we have the force of gravity of the student. The distances that were given for each one of these is that we know that the entire beam is 3 meters long, right? So we know that that's 3 meters. We know then the force of gravity would be at the equilibrium or at the center of gravity at 1.5 meters. And we're told that the student is standing 2 meters from the edge, from the left support or support 1. So that's 2 meters here. So those are all of our distances. So what we can do in this situation, remember that we get to pick where we want the fulcrum to be, through which we're going to assume that the torques. But before we even talk about torque, let's what we know, look at the summation of forces in the x and the y, and then our torques. So what information do we know? And what are we looking for? So we're told that the mass of the student, right? So I'm going to put MS is equal to 78 kilograms. We're told that the mass of the beam is equal to 100 kilograms. If I take N1 to be our fulcrum, to be the pivot point, and I'm going to do that so that I can eliminate N1 from being in our torque equations, then I can list my R values. If that's my pivot point, then the R value, or the lever arm of the beam weight, is equal to 1.5 meters. The lever arm of the student is going to be 2 meters. And the lever arm of N2 is equal to 3 meters. So that'll tell me my distances that each one of those forces are away from the pivot point. Okay, so picture, listing all of the forces, label what you know, what you want to know, and those lever arms, you must decide your pivot point. I'm choosing the place of N1 to be our pivot point to eliminate that there has to be an R value for N1. So once I decide on my picture, what I know, what I want to know, I can now make these generic equations up here fit my problem. So let's make those fit our problem. We obviously have no forces in the x direction. So if we were to do summation of forces in the x equals 0, that is not necessary in this problem because we have no forces in the x. But if you did in your problem, you would go ahead and summation of the forces in the x. So here we have static equilibrium. So we then know that the summation of forces in the y are equal to 0. Again, we're going to take up to be positive, down to be negative. So if I add up all of those forces in the y direction, looking at my picture, I'm going to have the force of gravity of the beam acting down, so negative the force of gravity of the beam, plus negative the force of gravity of the boy, of the student, okay, plus N2 equal to 0. Whoops, take that back. It's just the forces in the y. We have plus N2 and plus N1 equal to 0. So we have 4 forces acting all together. In the torque equation, if I say that summation of my torques must be equal to 0, I will take clockwise to be negative and counterclockwise to be positive. The pivot at the N2. So as I take a look at this bar, so remember we're going to have our bar, here's our pivot point, right? If the force of gravity of the beam is acting down, that's going to cause a clockwise torque. The force of gravity of the student, clockwise torque. N2 acting up is going to cause counterclockwise torque. So as I add these together, I'm going to say that the negative, the torque due to the force of gravity of the beam, right, plus negative the torque due to the force of gravity of the student, plus negative or positive the torque of N2 must add up to be 0. So the torques due to each one of those forces. Making the torque equations represented in force and lever arm, then this equation would become negative the force of gravity of the beam, right, times the lever arm of the beam, across the lever arm of the beam. I've already considered their directions, so we're going to kind of drop our vector notation after this, plus negative the force of gravity across the lever arm of the student, plus N2, which is my force, and the lever arm of N2 equals to 0. Now, what I notice in all of those, so again, the cross product is these are my lever arms, these are my forces, so they, for all of them, are at right angles to each other. So in the cross product of the sine of the angle between them, that is going to be of sine of 90 degrees, right? Equal to 1, so we're just going to ignore that in our problem. And we see that what do I know here? I can find that. I do know that. So I can find the forces of gravity. So the only unknown here, and I know this, is N2. Whereas in this equation, I have 2 unknowns. So I'm going to begin with this equation first, since I have everything that I need to know. and then put that into my previous equation with the summation of forces in the y. So rearranging this equation to get N2 by itself, I'm going to add these to both sides. So I'm going to add my force of gravity of the beam times my lever arm of the beam. I'm going to add my force of gravity of the student times my lever arm of the student. So I apologize. I see that those are not written correctly. That shouldn't say beam. That should say student. Right? On both sides. So that's going to equal, on this side, I add those over there, right? So on this side, I have that's force of gravity of the beam, lever arm of the beam, plus force of gravity of the student, lever arm of the student. So those get crossed out on this side. Doing our algebra then, we have N2 lever arm of N2. So again, we've done the cross product. We can drop that. These are the magnitudes of those forces, is equal to the force of gravity of the beam, lever arm of the beam, plus the force of gravity of the student, lever arm of the student. Divide both sides by the lever arm of N2. And you get the value of N2 to be force of gravity of the beam, lever arm of the beam, plus force of gravity of the student, lever arm of the student, all over the lever arm of N2. Okay, so remember, we've already considered direction, coming up here with the negative values and positive values of our torque, being clockwise or counterclockwise. We consider the cross product, which is what the torque equation is the cross product between the force and the lever arm. The definition of the lever arm being the perpendicular distance to the line of force. And we can see in our picture that our radius is given in the problem are perpendicular to the line of force. So that angle would be 90 degrees. So we've dropped that notation to just use the magnitudes of our forces, and this sine of 90 degrees would be 1. So now we can just put in the equation for the force of gravity, which is the mass times g, right? So N2 is going to be the mass of the beam times acceleration due to gravity times the lever arm of the beam plus mass of the student, acceleration due to gravity, lever arm of the student, all over the lever arm of N2. So I'm just going to factor out the g because it's with each term. And I'm going to say g times mass of the beam, r of the beam, plus mass of the student, r of the student, all over r N2. So N2, the support at 2, is 9.81 meters per second squared times 100 kilograms times 1.5 meters plus 78 kilograms times 2 meters divided by 3 meters. And all of that in, we would get N2 equal to, rounding it, 1,000 newtons, 999.9 newtons. We'll round that up to 1,000. Okay. So again, we solve for that based on the idea that when I established our equations, this equation I began with, because it had only one unknown, the equation with the summation of forces in the y had 2 unknowns. So we are now going to take this value and treat it as a known value to say N2 is equal to 1,000 newtons. So now I can just plug that into this equation and solve for our N1. So remember, N1 did not show up in our torque equation because we chose the pivot point to be where N1 is being applied. Any force going through a pivot point causes no torque. So plugging these numbers in here to solve for N1, we would rearrange the equation to subtract, and we're going to add force of gravity of the beam. We're going to add the force of gravity of the student, subtract off N1, right? And put that on the other side of the equation. So that's going to cancel it out over here. We're going to put them to the other side. Did they get the equation to be N1 is what we're looking for. Oh my goodness. We're going to subtract out N2. Equals force of gravity of the beam plus force of gravity of the student minus N2. So rearranging that equation. So now I get N1 is equal to mass of the beam, acceleration due to gravity, plus mass of the student, acceleration due to gravity, minus N2. So again, we can say G times mass of the beam plus mass of the student minus 2. So 9.81 meters per second squared times 100 plus 78 kilograms minus 1,000 newtons. Plugging all that in, you get the value of N1 to be 744. So our two forces of support are not the same, which might be what you would think at the beginning if you would look at this problem, that each one of those supports would be the same, but they are not, because the person is located at different positions, right? So if I go back to our picture, being that the person is standing closer to the other support, that one provides more upward support than the other. This is why as he slowly walks to the right, there would be more and more support on N2, and N1 would decrease down to the point where it may even be 0, and the beam would flip, right? So always think physically, what are the implications of the values that you're taking a look at? If this force of gravity moves over a little bit more, N2 would increase, right? Because your R value for the force of gravity of the boy would increase away from N1, causing there to be greater torque from N1. And then if that value increases, the N2 value takes away from the N1 value, to the point where if the two end up equaling right here, right? If these values, as this value increases, your mass isn't going to increase, but what's going to happen is this lever arm will change over here. All right, hopefully this helps you in solving problems with static equilibrium.